下面有请主讲嘉宾 Omar M. Yaghi. Please welcome the distinguished keynote speaker, Omar M. Yaghi.
Thank you very much. Let me start by saying that chemistry is about atoms and how atoms are connected to make molecules. And today I want to tell you what happens when you start thinking about how to link molecules together by strong bonds to make new materials. That's the research that we have been pursuing for the last almost 30 years, which has resulted in a whole new kind of chemistry we call reticular chemistry. And I've titled my talk An Infinite Frontier because indeed, as I will show you today, that it has resulted in an almost infinite number of materials and chemical structures. So today I will tell you a little bit about this chemistry, as well as towards the end, I will share with you a very important application that we have discovered dealing with harvesting water from desert air. And so reticular chemistry is defined as the chemistry of linking molecular building units through strong bonds to make crystalline extended structures. And there are three components to this definition, and each one has been a new development. One is that linking molecular building blocks, meaning that we want to be able to design materials, make materials by design to meet a certain specification that we want. Strong bonds, meaning that the building units are connected together with strong bonds so that you can make robust materials that could be placed in a power plant to capture carbon dioxide before it reaches the atmosphere and can stay there month after month, operating year after year. You don't have to change it every time it traps carbon dioxide. And we also want them to be crystalline so that we know exactly where all the atoms are and they can be characterized down to the atom and molecular level. So using this strategy, we have been successful in taking inorganic units, such as the blue clusters you see on the screen, linked by organic units, which are the hexagons you see there, to make extended structures. And when I say extended structures, I mean structures that if your eye can see a molecule, they are infinite structures. The yellow ball indicates the space within which one can trap, as you will see later, water or carbon dioxide or hydrogen. So these are called metal organic frameworks, or MOFs, and for short, they are now referred to as MOFs. We discovered them in 1995 and showed that they are truly porous in 1998, and then their porosity broke all records in 1999. We also made covalent organic frameworks in the same way, where you can link now, instead of inorganic and organic together, all organic through strong bonds. And then, if I have time, I want to share with you how we were able to weave molecules on the molecular level to make what one could call molecular cloth, the first of its kind in the history of chemistry. Just a word about how do you make these materials. They're simply made from the organic acid with a metal ion, and then you put them together in an organic solvent. Now we can put them together in water, actually, and heat up this mixture to make crystals. And making the crystals is, it sounds easy here, but when we first discovered it, it was not as easy. But now it is routine that we can make these as crystalline materials. These are the conditions under which you make a MOF, and they are being employed until today in making these extended structures. Now, what is special about a MOF is the unit that I am circling here in red. This unit is called a secondary building unit, and because it's a multi-metallic unit and it's chelated by the organic, it acts as an anchor to give the whole structure architectural robustness. So that now when you have the pores do not collapse in the absence of molecules filling up the structure. But the other thing that is nice about these clusters is that if you know the chemical conditions under which to make them, then you can add various linkers Some of them functionalize and some of them longer. As you see here, some of them longer to make functionalized pores as well as expanded pores. And this was a very important development early on because it showed that you can make crystals in which you can go in and tweak or design their functionality and expand their pores. Well, using the strategies that I just described, one can employ much more than the metal oxide unit that I showed you, the SBU that I showed you. You can have a whole array of metal oxide units chosen from almost the entire periodic table, linked by organics, such as what you see here, simple units, or they can go up to more complex units, as shown here. These link along two directions, just like a strut, to make those extended structure MOFs. And they can be ditopic, they can be tritopic, so that you can have different branching units to make different extended structures. They can be tetratopic units, more tetratopic units, and even the linkers, as you can see in themselves, could have openings and pores or metal binding sites. More tetratopic units, chiral structures, enantiomerically pure structures. Pentatopic units could be used to make MOFs. Hexatopic units, and octatopic units, dodecatopic units. All of these are organic molecules that you can link up with metal oxide units to make MOFs. And the reason I went through this exercise is to show you that if you can think it, you can make it. And the chemistry works. So we have to basically illustrate this in a periodic table of reticular chemistry, where now you can imagine, it's almost like Tinker Toy chemistry, where you can imagine a building unit of one composition linked by another building unit to make these variously shaped frameworks. And each square is a framework in which you can vary not just the composition, but also the metrics of the system. You can see different building units on the left that can be combined with the building units on top. And fortunately for the young people in the audience, there are still some open squares that can be filled in, so which would require some of you to go into the lab and try to make those. Well, the porosity of these structures was revealed to us after we studied how gas interact with the interior of the MOF. And it turns out that the yellow spheres you see on the screen are gas molecules that interact with the organics, with the face of the six-membered rings and the edges, as well as the metal oxide unit. So in fact, everything you're looking at in a MOF, whether it is the metal oxide unit or the organic units, is an adsorptive site onto which gases can be compressed. So these are, you can think of them as parking spots for gas molecules. As you know, gas molecules like hydrogen and methane and CO2, they don't like to come together. They like to be away from each other, so they fill very large volume. So in order to bring them together, normally you would have to go to low temperature and high pressure. But when you have a MOF, they are attracted to the internal surface of the MOF, and therefore you don't need to cool them down to energy-intensive temperatures or high pressure. The surface area of this structure in 1 gram of material, 1 gram of material is no larger than this. In 1 gram, you have a surface area of an entire football field, 6,400 meters square per gram, which means that if I take that 1 gram and I unravel it on the atomic level, I would cover an entire football field. And that gives you an idea of how porous these structures are. This is the Cal football field. So that's 1 gram of material covers an entire football field. Well, not only can you make extremely high surface area materials, but also you can expand the pore opening. The pore opening is very important because if you have a small pore, you can bind gases, but you can't bind large molecules like large organic molecules, maybe cleaning them out of water, or proteins, for example. So we have demonstrated that you can make MOFs progressively in larger and larger pores, as you see here. And the pores can get so large that you can bring in enzymes, and in this case, you can see GFP, a very large protein, can fit inside the MOF. So this brings MOFs to a whole new realm of chemistry, which means that you can now incorporate organics and proteins and be able to carry out reactions or isolation of these within the pores. So my message here for MOFs is that it's infinite chemistry that works, and it produces infinite materials and infinite application. Let's just do a mental exercise and say that we have 1,000 inorganic building units. Of course, we have a lot more than that, but I'm going to be conservative and say that I have 1,000 inorganic units, and I'm going to link them with around 1 million organic units. We have more than that, but as I said, I'm going to be conservative, and then functionalize them with 1,000 side units. They all will fall in over 1,000 frameworks. And so this chemistry is truly infinite. So in the history of chemistry, there hasn't been anything like it. We have combined organic and inorganic, two areas of chemistry that are taught separately, practiced separately, into one field that incorporates pores within which you can manipulate and hold matter to produce infinite chemistry. Well, this explains the extremely high activity in this field. These are the number of publications in MOFs over the years have shot up. And just last year alone, over 7,000 papers have been published in this area. And the exciting part is that now, globally, we are exploiting these MOFs. And you can see from the number of patents and the increase in the number of patents that are being filed on MOFs. Well, what about organic molecules? What about linking organic molecules together? There was nothing, no extended structures based on organics. As this statement says, in 2 and 3 dimensions, it is a synthetic wasteland. This is something that we have been able to address by linking organic molecules together to make what is called covalent organic frameworks, or COFs. These COFs, again, we found the right conditions under which to make these COFs in crystalline form. We can make them as 2-dimensional structures, but also as 3-dimensional structures by starting with 3-dimensional building units and linking them together to make extended structures. What I'm trying to tell you today is that chemistry has always been about molecules, metal complexes and organic molecules, and today I just showed you how these can be linked together to extend chemistry beyond molecules into the extended 2D and 3D regime. Well, one more thing. Once you have control of molecules and of chemistry on the atomic molecular level, there is no limit to what you could do. So weaving is something that humans have done since the beginning of time. And it's a very old way of making cloth, and it's still practiced today. It's still practiced today to make resilient materials. Our clothes are resilient. They can bend without breaking. Can we make structures, chemical structures that can do that? Okay? So weaving is basically interlacing of threads in and out of each other. They're held together by mechanical bonds. Okay? And so they can bend without breaking because you're moving them with respect to each other through mechanical interactions. So can we make structures of this kind? If you ask a chemist this, they will say, absolutely not. How are you going to take threads, throw them together, and have them form structures of this kind where you have periodic arrangements of these threads? Well, reticular chemistry, because reticular chemistry is based on the building block approach, could be utilized to make these structures. All I need is a crossing. Okay, if I can make a molecule that's a cross, as you see here, then I can link the crosses together to make a woven structure without actually having to weave the threads in and out of each other. And that's exactly what my students were able to do. You see here, there is a copper-1 ion that brings these mutually embracing molecules together, and then you use COF chemistry to polymerize them and make an extended structure. This is a crystal structure in which the threads are brought together by the purple atom, which is the copper 1, to make crystal. Okay? And the nice thing about this is that if you don't want the metal there, you can remove it. When you remove it, you've made basically an interwoven molecular cloth. And we know the structure of this cloth. And if you add the copper back, if you want the crystal, you can add the copper back and get your crystal back. And so you can repeat this in and out for the copper to make this woven structure. You can see this is crystalline, you can see crystalline cloth. And you are looking here at the very first molecularly woven structure in the history of chemistry. And it's done through very simple reticular chemistry. You can see the blue threads weaving in and out of the red threads. The reason this is important is because when we think about solids, we think that they're not dynamic. So now you can imagine with the MOFs and the COFs, what we've done, we've made robust structures that can also be dynamic and resilient. All right, so let me now turn to talking about one application. And I mentioned there are many different applications involving storage of hydrogen, methane, carbon dioxide, and water. So I want to talk about water today. So this is, in this map, the regions of the world that are orange and red are water-stressed regions. That means that they don't get enough water to satisfy their needs. They're in trouble. Okay, that's around 1/3 of the world population lives in those regions. And in the year 2050, there will be 50% of the world population will be living in water-stressed regions. And also, 160 countries import their water. That should be of major concern to those countries. Fortunately, from our point of view, there is plenty of water in the atmosphere at any time. There's 3 sextillion liters of water in the air at any one time. So this is a natural resource. If we can find a way of trapping water from the atmosphere, concentrating it and condensing it so that we can use it for drinking, for agriculture, then we would have solved a major societal problem. Remember, without water, you can't live. And if your water is not clean, then that means you're not going to be healthy. So water is a very, very important, maybe water is the most important problem facing our planet. So what is out there in terms of harvesting water from air? There are these devices that you can buy for thousands of dollars, but they all operate at high humidity, at a humidity greater than 60%. But the red and orange areas I showed you are areas of low humidity. That's below 60% relative humidity. There is no material that can take up water from low humidity. Well, there is no material that can take up water from low humidity and also release it in an energy-efficient way. So this basically tells you that the dehumidifiers that people use in the humid regions cannot work in any of those red areas that you see on the screen. And that's a big problem. So why is it that we can't harvest water from low humidity? Look at this psychrometric chart. The red line is at low humidity, and it tells you that in order to fill the air in a bottle, let's say, with water to condense it, you have to go to very low temperature, below 0 degrees Celsius. Well, that is very energy intensive. So that's not desirable. Our idea is that if you could harvest water from the air with MOF, then you concentrate the water in the pore and you create the green line. You basically create high humidity in that bottle. And now you don't need to cool down the air too much to be able to condense and collect the water. So what I'm trying to say is that you can take dry air with a dewing point of less than 0 degrees Celsius and low relative humidity and put it in a desiccant like MOF, And by doing so, you create high humidity, 50% relative humidity, and a dewing temperature around room temperature. Now you can condense humid air very easily. And that's exactly what we discovered with one of the MOFs. You can see in the red line that this MOF takes up water in a cooperative fashion at relative humidity around 20%. The fact that it is a sharp knee there tells you that this material loves water. So as soon as the first few water molecules go in, the rest comes in and fills the pores. The other spectacular thing about this material is the green line, that you can take the water out at low temperature, at 45 degrees C. Well, if you can take it up at 25 degrees and take it out at 45 degrees, that's basically the day and night temperature. And so that gave us the idea that perhaps you could use MOFs to create drinking water from low humidity. So you can see here that after many, many cycles, the MOF remains stable. The behavior is retained after, in this case, after 80 cycles. But notice that there is a drop. After the first cycle, there's a slight drop. What is that drop? If you look using X-ray diffraction and neutron diffraction at the water molecules in the pores, you see that the first water molecules cluster. They make tetrahedral clusters. They're shown in red there. And those red cubes you see on the screen are seeds. These are seeds of water. These are fragments of ice onto which other water molecules are attracted through hydrogen bonds. So basically, these seeds allow you to bring the water from the atmosphere into the pores. Well, does it work outside the laboratory? That's what we wanted to find. And what we did is we designed a device no bigger than this. And it's nothing more than just a small bottle. And on the inside of the lid of this bottle, you have the MOF. At night, you expose the MOF to the atmosphere. It takes up water. During the day, you close the bottle, and the interior of the bottle heats up when it's in sunlight. Water comes out, hits the walls of the bottle, and you make water. You can see here on this orange panel small droplets of water. And as the interior of the bottle heats up, the droplets become larger and larger. Okay? It works. It works outside the laboratory. We have created droplets of water from low humid air. Okay? But this is based on 2 grams of MOF in a device, in a small device. So it's not enough for drinking. So what we've done is we've created a box within a box device. The interior box is the MOF box, and at night, air goes into that box, saturates the MOF with water. During the day, you close the outside box and you expose it to sunlight. Water comes out of the pores, hits the walls, condenses water. Very simple. A box within a box, a plastic box within a plastic box. Okay, this is the device. This is the device that's going to deliver water. Okay, and you can see my students took this device with 1 kilogram of MOF to the desert in Arizona. And they collected, in one cycle, they can collect 200 to 300 milliliters of water without any energy input aside from sunlight. Okay? This is 1 kilo delivering enough water for you to live in a desert, to survive in the desert. If you want more, you can have 10 kilos, and then you'll have more water. Okay? The water that you harvest is extremely clean.
All right, ready?
Okay, it's ultra
2,
pure. This student is
3,
going to drink it.
Action.
Cheers.
Okay?
Nice.
Eugene survived all of this, and he's now part of a company that is commercializing this technology. The water is ultra pure because the MOF is a natural filter. okay? Meaning that the pores of the MOF don't allow anything other than water in. So if you have any other contaminant, organic contaminants, they will be rejected by the MOF. So the beautiful thing about reticular chemistry is that you can always make better MOFs. The MOF that I just showed you is a zirconium MOF, and zirconium is expensive. So we go to aluminum MOF. Aluminum is dirt cheap. And we make a MOF that actually takes up more water under low humidity. Okay? We design a different kind of device here, a device that has trays of MOFs, and in one direction air goes in the other direction you can harvest the water. I want you to focus on the blue line, the relative humidity, and you can see that in this experiment the students took the device to the Mojave Desert for testing. The Mojave Desert is the driest desert in North America, and you can see that the humidity during the day can go down as low as 7%. And you see from the bar diagram that they're harvesting water during the night and during the day. Okay, they interfaced. So this is the water. This is just a picture of the water that's being harvested from the atmosphere. They interface the device with a solar panel so that they can do more than one cycle. The solar panel provides power for fans to push air through the MOF and for some heating to 60 degrees Celsius to remove the water from the pore and run this several cycles. In this case, they harvested 1 liter of water per kilo of MOF. So much more than the passive device you can see at low humidity, 5 to 35 relative humidity. This is the behavior of the water uptake. If you look here, you see that it takes up water at very low humidity. This is around 7% relative humidity. The amazing thing is that when it releases water, look at in 5 minutes, you can remove all the water from the pores. 5 minutes at 85 degrees Celsius. 5 minutes means that every 5 minutes, I can run a cycle. So I can get 1 liter per kilo per cycle. Okay, now you're talking about significant amount of water. Okay, in this experiment, this is a device that's as large as a small refrigerator or smaller refrigerator, but now you see there is rain in the box, okay? This is water being harvested and cycled at the rate that I was talking about. Okay, this is water being harvested from the atmosphere in California at low humidity. You see the droplets are increasing in frequency, and now if you go down, you see the water running into a container, okay? It's a low-budget video, so I hope you pardon that. Okay, that's water from the atmosphere. Look at where we were, our productivity, with the first proof of concept device in May of 2016. We're at 0.001 liter per day per kilo. And then at the Berkeley device in September 17, we're harvesting 0.2, 0.3 liters per day per kilo. And the device we tested in the Mojave Desert, 1 liter. The device I just showed you, 10 liters. And if you work with very clever engineers, you can we hope to be getting 100 liters per day per kilo. Now you're talking about real water. That's a commercializable product that will be delivering near 100 liters per day per kilo. So this is what we're aiming to do. You can choose the amount that you want to deliver per day. If you just want a small device that you put in your office just for drinking, 4 liters per day, 2 liters per day, you just have less MOF, okay? But if you want a device that can provide enough water for, let's say, a home, then you can get a device of this kind. Our aim is to also be able to have devices that are large enough to supply an entire village with water. So what have we done? We, by discovering this water harvesting with moths, what we've done is that we will make water distributed, okay, mobile and off-grid. And we will make it personalized, because now you can, each one of you will have their own water harvester that can go wherever you want. Okay, it can stay in your bedroom or in your kitchen, and you can have all the kind of flavors you want if you like. And it's ultra pure. This is quite transformative, because now you are in control of your water. And you can get your water without control of anybody else off grid. So I want to acknowledge the funding. I want to acknowledge my wonderful group members, and thank you for your attention.
感谢嘉宾的精彩分享。Thank you for the wonderful sharing.